My name is Nicholas Dwork, and today I'm going to be introducing you to the concept of compressed sensing. Compressed sensing is another way to accelerate MRI. With compressed sensing, we reduce the number of samples collected for a faster scan. Compressed sensing then incorporates information that we've learned about natural images into the reconstruction process. It's a phenomenological thing. We believe that natural images have certain properties, and we're going to incorporate those properties into the reconstruction process, but there's nothing physical about it. There's nothing that mandates that natural images have those properties. It's just something that we've noticed over time. There are two tricks to compressed sensing: random sampling and compressibility. We're going to talk about both of these, but we'll start with random sampling. So here's a picture of K-space for a particular image. And this is the corresponding image. This is a sagittal reconstruction of a knee, and this is the image that you would get if you were to collect all of the data. One way to reduce the number of samples is to eliminate entire columns of data. So here I've collected just 1/3 of the original number of columns, so I've kept every third column and I've set all the other columns to 0. And if we assume that the values we didn't collect are 0 and then perform a reconstruction, this is what we get. This is not diagnostic. It was a much faster scan. It was 3 times faster because it only had 33% of the samples, but it's really, really difficult to see many of the details in this image. It's hard to even know what you're looking at. So a trick is random undersampling. Rather than eliminating entire columns or entire rows, what we do instead is sample with a variable density. So we'll sample randomly, where most of the samples are going to be located near the origin in K-space, and the samples will dissipate as we get further and further away from the origin. And if we do the same thing, we're going to assume all the samples we didn't collect are 0 and then perform a reconstruction. We get this. And somehow this is a lot better. What's happened is, rather than having the errors all stack up in a coherent way so that the resulting image is the original image plus shifted copies of itself, with random undersampling, the errors dissipate across the image, and so it becomes much more intelligible. However, this is still a bad image. Don't worry, we've got another trick: compressibility. So here again is the fully sampled reconstruction of the knee. What I'm going to do is take this image, shift it by 1 pixel, and then subtract 1 from the other. So I'm going to shift it a little bit horizontally and then subtract 1 from the other. And when I do that, I get this. This is a horizontal difference image. This is a simple way of doing what's called an edge detector. And what you notice, of course, is that the bulk of this image is very dark. It's nearly black. And this is true of all natural images. If we take a horizontal difference and look at it, it'll be almost completely black. We could do the same thing vertically. We get the vertical edges, and again, it's almost completely black. This relates to concepts of compressibility. If we know for a fact that the first difference images are mostly black, then we can incorporate that into the compression or reconstruction algorithm. So the reconstruction process with compressed sensing is return the image that does 2 things. 1, matches all the data that we've collected. So we want to make sure that whatever image comes out, if we were to take its Fourier transform and look at the values that were collected, they would match. But also, make the horizontal and vertical differences as dark as possible. And now our computers can solve this problem very quickly and very well. Okay, so here's the variable density undersampling pattern for compressed sensing. And here's the zero field reconstruction. So here's the reconstruction if we assume that all the values that we didn't collect are 0. Now I'm going to show you the result of the compressed sensing reconstruction. And you can see it's much better. Many of the errors have been eliminated. And if we compare that to the original fully sampled image, we see that it's very similar. This is a highly diagnostic image. It's not perfect, but it's very good. And so it comes down to what's important to you. Do you want a faster scan that's more robust to motion? Then maybe compressed sensing is important. If you have a young child who you don't want to anesthetize to scan them, and you think a faster scan will yield a higher quality, then maybe compressed sensing is the way to go. If you have an adult patient, scan time's not an issue, they're not having trouble sitting still, and you're not imaging any moving anatomy, then maybe you do the fully sampled reconstruction and get the highest quality image possible. Thank you for your attention.